So this would be like a graph version of this, but this has strictly less information.
I see.
Because I don't know who fed in where here,
okay.
right? So if you want to know where, like, this is not good enough for understanding.
What's the information for this one?
In this picture here, I had one, I kind of swapped them. Like this guy is going to the second port, whereas this one's going to the first port. In this one, I can't tell who's going to which port.
Oh, okay.
Yeah.
So if I'm understanding this correctly, because these are props, the strings, like you count the number of strings basically go in, and that's 4 or 5 or something.
Right.
Okay.
Yeah, that's right. So I cannot label the strings with anything that differentiates them from each other.
Okay.
But I still can keep track of where what their position is. Did someone else have a question? Okay.
Just a clarification.
Yeah.
So acyclic just means that the reduced graph is acyclic.
Yeah, that's right. So there's no cycles here. I can't get to any loop, any point from itself. Can't get from a point back to itself. Okay, so I'm going to tell you what free props are. How am I doing on time?
You're a touch slow.
A tad slow. Okay. So free props. Given a set G generators and functions in from G to the naturals and out from G to the naturals, the free prop on G is the set, is the prop, which just means monadic category where you can draw these kinds of pictures, but I have to tell you what kind of morphisms you get. And the morphisms are labeled, G-labeled port graphs. This is called the free prop. And what does G-labeled port graphs mean? It means I start with a port graph, which means you can either think of as like a set, 2 functions, and an isomorphism, or you can think of it as a picture. But I do one more thing, which is I have a labeling function, L, that takes every vertex to an element of G, preserving arities. What does that mean? Every V had an in and an out. Every V had an in and out cardinality or number. Every V gets a G label. Every G has an in and an out cardinality. And those diagrams should commute, which just means if I look at a V and I look how many things it has, that better be the same as the number of G's. If I'm gonna, so I'm labeling, I have G, so G might be this. G is the set G, H, and I. Every one of my G's gets an in, which is the number of input ports, and an out, which is the number of output ports. Just 2 natural numbers. So if I draw them like this, I'm kind of indicating what I want the in and out to be.
Is that map between V and G a bijection?
No. So what is going on is I'm allowed to write, what are the morphisms of this prop? It's any picture you can draw where you label your boxes with these labels. So for example, I could have G, G, J, and I. Oops. And because I have a port graph, and because everything's labeled with a label of the right sort, this would be a G-labeled port graph. And so what we're saying is that a free prop, if you give me a set of generating morphisms, you give me a set of boxes, and you say, here's a box, it's called G, it's really important to me, and this one's also really important to me. And this one are really great boxes. You can use them any way you want in a picture, and I'll be able to interpret that picture. So we'll soon do an example of this. Okay.
But each such picture is a separate prop.
And each such picture is a separate morphism in this prop, the free prop. So I've got one prop that is able to interpret any diagram like this. These are the morphisms in that prop. Okay, so why don't we...
So David,
Yeah.
so if you say one is baking and one is mixing, etc.,
Yep.
that means that I can kind of bake before mix, and that's an acceptable
Yeah, recipe.
process? It's an acceptable recipe?
Yeah.
Okay. So there's no ordering internally to the objects
Right,
to make this work. That's legit.
right,
I'm not going to do that, but
yeah.
So what two object is this a morphism between?
This is a morphism between 6 and 1. Because the morphisms are always the natural number. The objects are always the natural
Right
numbers. Okay, so let's go back to signal flow graphs. Signal flow graphs a free prop. So that was an example of a free prop all along. So what are the generators in this free prop? The generators are copy, scale. Well, I'll do that one in a second. Throw away. I don't know if I drew that one ever, but add and 0. I don't know if I drew that one either. Okay, so to give you a free prop, I have to tell you a set of generators and 2 functions for every generator, of which there's 1, 2, 3, 4, infinity. I have to tell you what the inputs are and what the outputs are as a natural number. So what's the inputs? Let's go up for in and down for out.
What are the objects of this category?
The objects of the category are the natural numbers. What are the inputs of this as a natural number?
1.
1 input. How many outputs?
2.
How many inputs?
1.
How many things are coming out?
0.
Here,
2, 1, 0.
0, 1, and here,
1.
1, 1. Right. Okay, so now we've specified our generating set and our in and out functions. And that's enough to give me a free prop. The free prop, what are the morphisms from one set to another set? Sorry, from one natural number to another. They're all the ways I could draw a labeled port graph with these as my labels. So I could go that, and that, and that, and
You know if these sets of morphisms are enumerable or not?
I guess, no.
No,
Not in this
it's
case because I have
it's
no
a real
menu.
number. Because that's a real number? Yep. But without that, would they be?
I don't know. I would say so. But
Up to...
so this is a port graph, but it's not labeled yet. So we could label. I only have one label that works here, which is written like that. I only have one label that works here, which is written like this. I only have one label that works here, which is, well, no, I have lots. And you might not be able to read what I'm writing there. And I only have one label that works here, which is the add one. But it's very kind of dumb to draw these squares and then put the really nice looking thing inside. What I'm supposed to do is just, that square was just there to help me and really so these pictures that we drew were morphisms in the free. Whoa, how come this guy never had one?
No.
Oh, that was a mistake. Okay, so these, does that make, can you read this thing? Okay. So labeled port graphs, labeled by these labels, are signal flow diagrams. That's what we were drawing all along, were the morphisms in a free prop. Okay, great. All right, why don't I let you guys discuss amongst yourselves to a neighbor and just see where you are with all this stuff. Props, free props, etc. Go ahead.
Sorry, you came in late. I'm Brendan. Catch up on what I missed.
If it's
Yeah, but I don't know. I don't think
Here's the
why
outline.
this
I get the fact that you don't want to do that, but it feels like
The main point
stronger sense that
of this lecture is there's these things called signal flow graphs, which were invented by Shannon, and they kind of look like this, and the way you understand it is they're sort of a depiction of how signals are flowing through some sort of network. So these things mean copy, these things, the white circles, mean add, and what it's saying is that if you put in some numbers, say 2 and 3 here, then you can track it through. So you get 2 copies of 2 there, you get a copy of 15 here, this adds to 17, this multiplies to 6. These ones are like multiplied. Yeah, these ones are multiplied, so they sort of, you think of them as amplifying your signal. So there's a structure that people use to solve systems of linear equations, and in fact, because of things like the Laplace transform, you can solve systems of linear differential equations, so they become quite useful in control theory and engineering. But these things are also sort of very naturally kind of fit into these string diagram pictures we've seen from the last couple of lectures. And so the question is, this lecture is sort of answering is, when you encounter this sort of system, something that looks like string diagrams, how do you understand these actually as string diagrams? How can you build in a custom way the category that you want? And then after you do that, what does that give you?
The fact that you pulled off that one, I was like,
So a prop is really quite simple. It's a type of monodal category where your objects just have to be the natural numbers, and your monodal product is addition. So if you think of, so the point is to move to a more simple structure than monodal category, because that's where these diagrams can be interpreted. And then we want to talk about generating things to construct the thing you want, just like you can draw one of these
Did anyone have a question?
graphs and call it a Hasse diagram that generates a poster. Now you can draw these generators and say, I want a prop, and then you get a prop.
Okay, yes. You have a question? Yeah. Okay. Say again? Yeah. Okay, so someone asked a question, and they asked, is there a notion of morphism between props and mapping between different props? And the answer is yes. It's a functor between the monoidal categories that sends each natural number to itself. So I have 2 different props. They're both monoidal categories, and both of them have objects to natural numbers. So as long as you give me a monoidal functor, it sends 1 to 1 and 2 to 2, then it'll be a prop morphism. And what that'll mean basically is that the labels of one will be sent to the labels of the other, and the composition of one will be sent to the composition of the other. So
And how do you make sure that that map to the n is still commuting when that happens?
That's going to be, it'll be a map from B to W.
Okay.
W will be going into these guys, and you'll ask it to everything to commute.
But
That'll be part of the
it's
rule.
guaranteed as long as.
That's guaranteed by the fact that it's a functor.
Okay.
Any other questions people had, or interesting discussions? Something you want to bring up? Okay. So one person asked, "Why is this interesting?" And that's a tough one. But I think there is something I can say about that. So the next thing is actually a prop morphism, or a functor, from signal flow graphs to matrices. So we can interpret a signal flow graph as a matrix. In general, so we'll give a functor like this. But in general, to give a functor, and by that I mean a symmetric monoidal functor, out of a free prop, one just has to say where the generators go. So for general props and for monoidal categories, etc., you have objects, you have morphisms, you have composition rules, you have identities. In a free prop, you have all that stuff too, but there's the minimal number of rules possible. So all of like the compositions and all the rules that make a prop functor hard to get don't get applied to anything when you have a functor out of a free one. Like nothing says stop. Everything's like, yeah, just bend me and mold me any way you want. I'm completely happy and free to do anything you want. So you can make 2 equal to 4, that's fine. Now 1 equals 3, that's fine with me. So you can make whatever things you want true to be true, and it will accommodate that. It has no restrictions of its own. So if this is true, if to give a functor out of a free prop, we just have to say where the generators go. And if we want a functor out of SFG, and if SFG, signal flow graphs, is a free prop, then in order to give a prop functor from here to here, we just have to say where the generators go. Okay, I just put those sentences together. Yeah?
So just a small thing. What you said is symmetric monoidal functor, right?
Yeah.
So I can imagine what it means to sort of preserve the monoidal product.
Yep.
But is being symmetric different from that?
No.
Additional.
No.
Yeah.
Not really.
Okay.
The symmetry on one has to go to the symmetry on the other. So if I take this guy and I compose with this guy, and I translate this one to some f prime, then doing this to f prime, sure. If I take f to f prime and I hit it with this, it should be the same as hitting it first and then going across. Does that make any sense?
Okay.
Yeah. It's very small. It's the kind of thing you would expect if you had one in front of you, you would expect that to be true. Okay, so, right. So to give this functor I guess, for interpretation. So what is I going to do to the copy? First of all, what sort of thing is it? Is it a number, a matrix?
What is big I here? What is big I?
Big I is my functor from an SFG,
Okay.
of which these are the generators, to the category of matrices, the problem matrices. It's a matrix. And what matrix? What sort of matrix?
1 to 2.
1 by 2. Okay, so what 1 by 2 matrix should it be? It should be the one that takes in an A, and when you're done, gives you A comma A. Right? Because this thing, if we remember what the semantics were, it took a signal and copied it. So it's going to be 1, 1. So I of this thing is going to be equal to 1, 1. Two by 1? Oh.
Yes.
Draw horizontal.
Oh, I'll draw it horizontal.
Yeah.
1 by 2. Thanks. Okay, so it's going to take 1 on the left and multiply by this guy. And we're going to get, it'll take A and give you A, A. Okay.
So this
So
is transpose matrix multiplication. Well, okay, yeah.
Maybe I'm in math off.
I think
that's okay.
You have with F compose G versus F.
Yeah,
or
it's the
NG.
same problem.
Yeah, it's always that order of composition problem. Okay. So what is I of well, it's a 1 by 0 matrix. And so there's only one of those. It has no entries. And what's I of this thing is supposed to take two signals and add them. And it's going to be a 2 by 1 matrix.
Maybe 1, 1.
It's going to be 1, 1. Yep.
Vertically.
The other way.
And what is I of this guy? This is the thing that, yeah, right. Takes no signal and returns something. This is going to be the empty matrix again, a 0 by 1 matrix. And finally, what is I of A? It's going to be a 1 by 1 matrix. I got a signal from someone. Please, you can do this. So I did. It's A. It's going to take in a signal, a one-dimensional signal, and return a one-dimensional signal. Okay, so why is this interesting? So what this says is now for any signal flow graph, like this, so here's a signal flow graph. This is going to be a 3 by 2 matrix. So I of this is a 3 by 2 matrix. Or is it 2 by 3? Which is it like this?
It has 3 rows and 2 columns, yes.
Okay. So what matrix is this? Well, let's say one person is following, they're taking X, Y, Z and returning these things. So that person is taking this going, okay, there's an X, 3, 6X, so they got 7X, 4, so we have 7, 4, wait, did I get it right? 4. And then they have 6, oops, wait, sorry, 4, 4, oh, 6, no, listen, 7, oh gosh, 6, 4, 4, is that right? Okay, so one person can fill it out that way. The other person translates something like this into matrices. So what you do is you take this matrix, actually you take this matrix is 1, 2, 1, 1. 1, 1. This matrix is 1, 1 that way. So this part here is that matrix. Do you guys read that? I did the block diagonal thing where I kind of put this guy and I put this guy and I put zeros everywhere else. So what matrix is this one? It's going to be a 3 by 3. What 3 by 3 is it?
1
1,
diagonal,
3,
1,
2.
3, and 2.
1, 3, 2. Agreed. And what matrix is this one? It's going to be a 3 by 2. 3 by 2. What matrix is it? 1,
1, 1, 1.
1, 1? Oops. And this one is like 1 and 2. And this one is like, I don't know, 1, 1, 1. So this would be very annoying to do. No one wants to look at this. No one wants to interpret this as matrix multiplication because that's boring and annoying. Like, look, this thing is this, where you just follow wires around and you make sense of it. So this is a very like visually simple, not only visually but for a computer I would imagine it. Well, I don't really know, but you might want to just trace through. I don't actually know that. I don't know that. Maybe it probably wants to do this actually.
It probably wants to do that.
It probably wants to do it. Yeah, that's true. But there's some difference. There's some way that this is a nice, convenient syntax for something. And so that's a reason that you might prefer looking at these to looking at those. Yeah.
This, where you sent these generators under
Yeah.
this functor, you chose because of this interpretation you
That's
discussed
right.
earlier. But it's
Right.
not the only functor.
It's not the only functor, no.
In fact,
So-
you can do anything, right?
That's
you can
right.
Send it to anything. Okay.
That's right.
Right.
So the signal flow graphs are syntax. And the matrices are semantics. So in the beginning I told you that you kind of like watch and see the contribution something gives. And so that was the intended semantics the whole time. That's like the meaning we're interpreting this as. A syntax is just a way of creating such things. And the functor gives our syntax meaning. But as you said, there's many different things that could have worked. I could imagine maybe if you like, well, yeah, not going to guess other functors, but anything else works. As long as you send this guy to a 1x2 matrix, this guy to a 1x0 matrix, etc., you will have a syntax. You will have a semantics. You will have a functor.
Right. So you could send the scalar instead of to A, you could send it to 7. Every
7.
scalar could go to 7.
And this one could go to that.
Right. And that would be a functor.
And then every time you saw this, you would know that one was being added to 3 times that one. Okay. Questions on that? Other questions? How am I on time?
You're 3 minutes low.
Okay.
Nice.
Okay, so the next topic, we talked about free things, but we can also talk about presentations. Free plus equations. So when you present something, you say, here are the kinds of things I can draw. Here are my generators. Here are how I labeled my boxes. That was one thing I said 3 different ways. Here's what I can draw. Here are my generators. Here's how I label boxes. I label boxes with generators. And all I can draw are boxes with generators in them. Okay, so that's free. And then equations say, but I promise that whenever you see this, that will be the same as this. I'm only allowed to say they'll be the same if they take the same number of inputs and have the same number of outputs. Otherwise, it doesn't even make sense to say they're the same. I could say they're the same. So I could say 0, scaling by 0, is the same thing as killing my thing and then starting up a new one with 0. Okay, so now, when you write down a presentation, you write down what you're allowed to draw, and you give some equations. And it turns out that in matrices, these equations do hold. This one you'd have to actually think about a little bit, because you're multiplying a 1x0 matrix by a 0x1 matrix, giving you a 1x1 matrix. And what happens is you do a certain sum over a certain index that never starts, and so you do the empty sum, which is 0. But aside from these corner cases which do work, everyone who does math, when you get above a certain level, you know that a sum with no index always gives you 0, and a product with no index always gives you 1. Like 0 factorial is 1 because you never start counting down, and 5 to the 0 is 1 because you never start multiplying. And that same kind of idea works when you have no things added together, you write down 0, and that's why these two things are equal. But regardless, what I mean by a presentation is I give you some symbols I'm allowed to write, and I give you some equations that I will always want to be true. And once I do that, that gives you a prop. So there's a prop that takes, if you have any presentation, meaning generators and relations, you get a prop. And it has a universal property like this one, which says, in general, to give a functor out of a presented prop, one just has to say where the generators go and check that the equations are satisfied in the other prop. That's how you would kind of add to this. So I could start writing down, and in the notes, which will be online after the class, I forgot to put them on before, I could write down 17, for some reason there are 17 known, or relations or equations people like to write for matrices. So what the 17 are, I'm not going to write them all. There's this one equals this one, as I said before. And there's like this one. If I start with 0 and I add it to A, I get A. So here's one. So I take two things and I add them, and then I split the result. Let's check that that's the same thing as taking my two things, splitting them, crossing them, and then adding them. So this one you have AB, and what do you have here?
A plus B.
A plus B, A plus B, right? Here you have AB, what do you get there?
A plus B.
A plus B, A plus B. So these are the same. And you can write down 17 weird looking pictures like this. Some of them kind of make sense, and some of them are kind of unexpected, but you read them out and you're like, yeah, that does work. And when you're done, you have this free prop, SFG, mod 17 weird pictures. And that's a prop. And all of those weird pictures, we actually check that if you put in a matrix, if you think of it as a matrix, you get the same matrix on either side of the equation. Which means there is a functor from this to that. The 17 weird equations or pictures are chosen such that this will still work. And in fact, this is an equivalence of props. I mean, they're basically the same prop. And so
Does
what
that mean that the functor is reversible? Or
The functor is reversible.
Invertible.
Yeah, that's right. The functor is invertible. You can go from a mat and get a weird picture, or a signal flow graph. And what this tells you is that this is called sound and complete. So these 17 equations, or pictures, are rewrite rules. They tell you if you have one picture, if you have some crazy prop, some propmorphism, some signal flow graph, and you can rewrite it using these rules, and you can rewrite it any way you want, and it'll be the same matrix. It'll have the same semantics. And so this is called sound, meaning anytime you can get from one signal flow graph to another, using these rules,